Hello, this is Sam in FreeRTOS. I'm here with the group. We're group Lab Section 2, Group 10, and our color team name is very light blue. Today we're going to be walking you through we're going to be giving you a system overview of the code that we used. So on the GitHub, this is our most updated branch. We come down here, we can see the table of contents, all our team members and all of that information. Description, just a very small description telling you what the project is about. Here we have some of the libraries that belong to some of the sensors that you would need to use, have. Those are the external ones. Unit tests, Bricks will be covering this later, but it just tells you where to find it. And then we have a little directory tree that sort of just illustrates the formatting of the code and the GitHub repo. So our code is in source. We go here. And here it is. Now it says .cpp, but it's because I have an IDE that's different than Arduino that you can develop out of. But it is, if you convert it to Eno, it works. And proof of this, we also have Arduino SAM branch. So I'm going to be walking you through the code. So the code starts off with our include. We did use FreeRTOS. Now, what's cool about our program is we have some program configuration. So if I were to set monitor power supply to false, it wouldn't execute. But what this does is it executes a routine where if it's true, it will check your battery if it's above 5 volts or not. If it's below 5 volts, then the program will not continue and it'll split on your serial monitor to swap your batteries before and then try again. Debug enable allows for the same sort of situation where we can filter prints when we serial print. So if I do debug enable and then LFS debug enable to true, then anytime I call this, it just serially prints. So that way, that also allowed us to do a little bit better integrated testing.
You forgot to mention what LFS means. What does LFS mean?
LFS is just an acronym for line follower sensor. And if you go down here, you have USD debug enable, which is just ultrasonic distance sensor, and so on and so forth. I've got another similar thing with calibrate enable, which is it will run a routine that you place the shoveler in position and it'll give you the analog reading of black and white tape, and it's good for floors that aren't exactly ideal conditions, so not purely white or purely black. So that's just about how you can sort of configure the settings. The optimal way to run it is to have monitor power supply to false and calibration to false once you've done that. So this is just some macros that instantiate our pins, and they're well formatted to be clear for the entire team. We've got some comments for some of the handler functions. So our first task will actually be explained by Amin.
We made a couple data structures. Those were specific for controlling the motor. So you'll see here we have vehicle move with some names like move, stop, forward, backward, left, and right. Those will be used in the translation task for us to see what motors need to be controlled to move forward, backward, left, and right. So going down, we also have another struct called the vehicle command. This simply specifies the speed and the type of movement that the robot will execute. This queue is an RTOS queue used to basically add a bunch of operations that RTOS will slowly take in. Sam will go into more detail about how it's being taken in and basically get executed so we can have our movements done in sequence. This is just getting the ultrasonic sensors distance. Okay, so our first one, drive motor. So drive motor takes our motor command data structure defined above, and then depending on the motor ID, since our robot had 4 motors, we'll have a specific direction with a specific pulse width modulation defined on the top. So we'll just keep going down here. All right, motor task. So this is where the queue really starts to shine. So we'll see here that this is in a constant while loop, and we're waiting on if something gets added to the queue. If something gets added to the queue, we control the motor. Now, if we keep going down, push motor command, that simply adds a command to the queue, which will be used in the translation task. So the translation task kind of works as an intermediary between our control logic and these motor commands. This guy will take in a given argument, and then based off that argument, it will send some motor commands depending on the type of, I guess, movement we want to execute on the robot. So you can see here that data structure defined above. Every single motor has a specific speed and direction. So we'll see for stop, it's all zeros. For move forward, it's all ones. And you can see we had 4 motors. 1, 2, oh, okay. And that's all for that. Uh, you want to talk about the FSM?
Sure. So
Okay.
I'll quickly go over the final task. So this is where this you can think of sort of as a producer and the last two tasks as receivers, as Amin was talking about with the queue. This command task will actually push the vehicle commands, which gets back into the task 2, which Amin explained, and then that'll convert it into the motor control stuff. And obviously those other tasks are higher priority. So this is where all the sensing happens. So this first, it's same format again. You've got a queue here in the specific data structure mentioned earlier. You've got some variables used and then repeating loop forever, and obviously FreeRTOS will cycle through. Over here, we just have the state transition logic, and the default state is to move forward. Then we have some checks based off of our sensors, which will change. If there's a line detected, it will change the current state to state reverse turn. So that's just the transitional state logic. And now in terms of the actual state logic, that would be right here, and that's just more so the implementation we use. So it would turn, stop, back up, and it's just more of the same. Setup is where we have some of those earlier functions where I said you can enable. So if this was enabled, yeah, and there's just more pin setups. So we're gonna have Bricks talk to you guys about the unit test that we did.
On the unit testing where I wrote test cases for each sensor, I took screenshots for each test cases of the serial monitor where they were doing the function that was intended or what we expected and compared them with the actual results. So now I'll talk about each testing and what we got for each of them. And so this is this is for the IMU where we tested the gyroscope, and then yeah, here's the results, the actual results that we got. And then this also for the IMU where we tested the accelerometer, and then the actual results we got, which were what we expected. And then this for the line sensor. Here we can see that when we went over the black line, that it sensed it. And then for the time of flight, here it is. It's detecting the obstacle that's in front of it. And then for the ultrasonic sensor, it does the same thing. Well, we had 2, that's why there's left and right. And then for the encoder, here it is for it working. But yeah, thanks for watching the video.